Welcome back, geographers. Welcome to our lesson today, which is session 4, being the last part of our grade 10 and 11 revision, which is part 4. We are going to be looking at, as we said in the previous session, we'll be looking at communication in geography, and that is very important for us to sort of think about how do we use representation, or what forms of communication methods are employed by geographers or climatologists, to be specific, when we are representing climatic conditions throughout the world. So I hope we are ready and excited, as I am, to have our session for today. Now, for starters, we'll be looking at our session outline. Of course, it says we will first look at synoptic weather maps. Now, what are we looking at synoptic weather maps? We'll first think about what components make up a synoptic weather map. We'll then look at the difference between a synoptic chart or map of showing winter conditions and summer conditions. We'll then look at how can you interpret weather station components, what are they, and how can you interpret them. And then we'll then move on to satellite images, where we'll be looking at what components make up our satellite images and how can you interpret them. We'll then move on now to showing you how we represent data in geography. And remember now our scientific process skills. You must remember our scientific process skills involving observation, inference, measurement, and categorizing, then communication. So you remember those scientific process skills. So those are the skills that are employed when we represent our data in geography, the data we collected using our scientific process skills. So we'll be looking at how can you identify the different hemispheres, how do we represent them, and what lines do we use in geography maps. So we'll look at what are contour lines, what are isobars, what are isohyets, and what are isotherms. So those are some of the things we'll look at in today's session. Without wasting any time, let's get to it. The first part, as we said, is looking at synoptic weather maps. So now we have to think about the components of a synoptic weather map. So before we look at that, let us define what a synoptic weather map is. Now, I've broken down the different weights. Now, the word synoptic maps or chart is formed by the weights first synoptic. Now, what does the word synoptic mean? It means a summary of a current situation, right? Now, a synoptic weather map, it means now it shows us a summary of a specific situation. And what situation are we looking at? It shows us a summary of the weather conditions at that specific time, right? Now, it means now as we are looking at weather, we need to understand what weather is. Now, weather means or is the state of the atmosphere at a particular place at a particular time, and with that we are looking at how are the temperatures there, how is the heat, how is the cloud cover there, how is the humidity over there, and how is the sun shining at that particular region, how is the wind speed at that region, and what precipitation do we have at that particular region. So a synoptic map basically shows us a summary of weather patterns at a specific time and at a specific place. Now, how do we represent this summary? We use a map or a chart. And what is a chart? A chart is a sheet of information that is represented in table form, in graphic form, or in a diagrammatic format. And we know that synoptic charts are diagrammatic in nature. That's why we refer to them as synoptic weather charts, because we use a diagram of that particular place to represent the climatic conditions of that place, or the summary of the climatic conditions or weather patterns of that particular place. It is also referred to as a map because we have a map in that diagram. And remember, a map is basically a diagrammatic representation of an area of land or sea showing the physical features, cities, roads, etc. So we don't really show the roads and all in a synoptic map. We just show you the differentiation between the different places of a particular region. So you must understand that's a synoptic weather map now. But in summary, then how would you define it? So you define that a synoptic weather map is a chart or map that summarizes atmospheric conditions. What are they? Those are temperature, precipitation, wind speed, and wind direction, atmospheric pressure, and cloud coverage over a wide area at a given time. So that's a synoptic weather map. And it has different components, of course. Now, what are those components? Those components are represented using symbols. The first component of the synoptic map is a symbol. So we have different symbols that represent different things. Now we use symbols to represent the precipitation. Now we can have drizzle, we can have showers. We represent using a triangle facing down. Drizzle is represented using a comma. Rain is using a full stop or a dot, like kind of a structure. Snow using a star. Hail is a triangle facing up. Thunderstorm is a K-like structure with a hat on top. And we also have heavy rain. Heavy rain is represented using 3 dots. Sleet is represented using a star and a dot. Snow shower is represented using a star and an upside down triangle for shower. Then mist is represented using a double equal sign, let's just put it like that, and fog is represented using triple lines, right? So that's how we represent a fog. So those are the symbols or some of the components we have. We then have circles representing cloud cover. Now when we have clear skies, no cloud cover at all, we have an empty unshaded circle. When we have 1/2 or 1 octave, we basically have a minimal clouds in the sky. When there is some level of cloud cover, we say we have 2 octaves. That's how we represent that. And we can have 3 octaves, 4 octaves, 5 octaves, 6 octaves, 7 octaves, 8 octaves, which is overcast, and a sky obscured, which is a mixture of all. So that's what you will have as the symbols, right, for cloud cover. So I'm not going to cover all of them, but I just want you guys to sort of remember the symbols you use in synoptic charts you are taught in grade 10. And then with wind speed, we also now connect we also connect our synoptic charts to wind speed arrows or feather-like structures, right? So when we have calm winds, we don't have the feather-like structure or the arrow. So you'll have double circles in that case. When it is 1 to 2 knots wind speed, we just have that long stick over there. When we have 5 knots, we usually represent it like that. Please don't use this one. Let me just show you which one to use, because it may be confusing. One may come and say this is 10 knots though. So there's something wrong with this diagram. Let me just represent that. So if it's 5 knots, you'll have your circle. Sorry, it's a bit skewed. And you'll have your stick. Now you draw your arrow from the central point. So that is 5 knots. And then if it's 10 knots, remember this is 5 knots. Ooh, my handwriting is funny. I'm using a mouse, guys. Sorry. When it is 10 knots, so when it is 10 knots, you have your circle and you have your long thing, and you just have that is 10 knots. And then this is sorry for that, sorry, yes. So this is 15 knots, so you have that long arrow and a short one. That's 15 knots. If it's 20 knots, both the feather-like structures are long. If it's 50 knots or more, you have a shaded triangle, right? So that is 50 knots or more. Strongest winds. So that's how you use the symbols. Another component we have on a synoptic map is isobars. Now, isobaric patterns rather. Now, isobaric patterns need for us to first understand what isobars are. So we say isobars are imaginary lines on a synoptic map that represent places of equal atmospheric pressure. So those are isobars. Now, you must understand that there are different factors then that influence the isobaric interval that you will have. So the first one is that South African coast has mountains, or it has hilly mountains in the coastal regions, and because of that it may have an influence on the pressure and the winds that we are going to have as a result. Now it means now our settlements in South Africa are located where, or are situated at the central plateau, and because of that we are going to have different patterns in pressure, because the plateau has an influence in climatic conditions, as we are going to see when we do subtropical anticyclones. And because of that, we need to have isobars representing what will happen to the air and how is this air elevated into the interior by different systems, right? So for starters, you know that at the interior in winter you'll have the Kalahari high pressure. In the Indian Ocean you'll have the South Indian high pressure, and in the South in the Atlantic Ocean you have the South Atlantic high pressure. Now you know that these circulate in an anti-clockwise direction. Now their circulation may lead to a specific representation of isobaric patterns being shown on synoptic maps, and that influences how we choose to interpret synoptic weather maps. So please take note of this, because it's very important. It's a very important component that you need to keep in mind or be cognizant of as you are studying this section of work. So let's move on. Now, what types of isobaric patterns do we have? Now, for starters, we have these specific isobaric patterns. Now, this is adapted from the Excellent Geography Study Guide, so we've credited it over there. So the first isobaric pattern we have is known as a ridge or a wedge, or what we call ridging. So ridging is basically the extension or elongation of what? Of a high pressure cell. So looking at that picture, we have a South Atlantic high pressure cell. So if it is further away from the country, it will extend towards the interior, and when it extends to the interior, we call that reaching or wedging. And it does that simply because our coastal regions are occupied by mountains. Remember that we said we have mountains. I'll use these lines to just represent our mountains in the plateau. So since we have mountains around the plateau, it will reach, and this reaching enables for air to be elevated into the interior. We also have what we call a trough. Now, a trough is the opposite of a ridge, right? So a trough is basically the extension of a low pressure cell towards the interior. For example, a mid-latitude cyclone would extend to the interior, and we call that a trough. And then we also have a circle. Now, a circle is defined as a zone of constant pressure between two low pressure systems. So you'll see that we have a coastal low and a mid-latitude cyclone. Those two are two low pressure systems. So, and they have the same pressure, and that is represented by the isobar over there. So the zone of constant pressure is known as a circle. So those are the patterns we have. Now, let's just try and identify them now on a synoptic map. So this is a synoptic map represented there. So I want us to just sort of look at some of those we've discussed. So I said we have what we call a reaching. Now, if you look at D, what is D? D is the South Atlantic high pressure belt. Now, it's the South Atlantic high pressure belt, and you see that it is a bit further away from the interior. And if you look at your interval, of course, you see that pressure is increasing towards the center, and the isobaric interval there is 4, right? Because we are adding 4. It's 4 hectopascal, but we are not there. The most important thing is the pattern that emanates from this high pressure belt. So you see it is extending. It's extending towards the interior over there, and that's what we call reaching or wedging. So it is wedging or reaching to the interior. So that's what we have over there. And let's also think about another isobaric interval that is shown in this system. So you see that here we have isobars in this mid-latitude cyclone, and this one we have isobars extending to the interior, and you see that that is a representation of what? Of a trough. So a trough, that's the extension of a low pressure system to the interior. So this is showing us how pressure is changing as the system extends to the interior. And something very interesting that we can see now is that we have this coastal low pressure, right? And this coastal low pressure, we have a line here taking us to this low pressure system, the SAC. So this line is known as a circle, you see that. So all these patterns are used in your synoptic weather maps. So please know that, remember, it shows us that we have constant pressure from this system to that other one. So that's what we call a circle. So you can see that when you talk about these lines, guys, they are not imaginary. We can actually, they are not self-made or just sketched for fun. They actually exist. They are used in your synoptic maps, and you need to know them because if you are to study your synoptic maps and understand them, then you'll have to sort of understand fully pressure differences within the two systems. And just to show that the pressure is really the same, because remember, a circle shows a zone of constant pressure. If you look at this line, it takes us here, right, to the system, and we have the isobaric interval of 1012 hectopascals, right? And then the next line after that is this one, and it gives us what? 1008 hectopascals. And now at the center of this coastal low, the interval there is 1004 hectopascals, and that's the same as what we have in this mid-latitude cyclone. That is not fully clear in this diagram, but that's the one. So it's showing us that this is indeed a circle, because it shows us the zone of constant pressure. There is constant pressure between these two high pressure. What's this? Between these two low pressure systems. So please note that, please remember that for examination purposes. Thank you very much. I hope you understand that. Let's just move on to another component. Now, synoptic weather maps, of course, will differ in summer and winter. Now, how do they differ and what components do you look at? Now, this synoptic weather map is showing us typical summer conditions. And what can we first use for that? We can use the dates, right? So this is the date. It's 17 February 2020. Now, 2010, sorry. And this is in the southern hemisphere, right? And we know that, how do we know that? This is a map of South Africa being shown there. So it shows us that this is indeed in the southern hemisphere. So what you identify then in this diagram is that how do our seasons go in the southern hemisphere? We know that our spring, maybe counting from spring, our spring starts in September. So from September, October, November, that is spring. From December, January, February, that is summer. And we know that it is summer because of the date being February. If you were to give visible evidence from the synoptic map, you'll give that as evidence. What else can you use? Something else that you can use is the location of the thermal low. There is a thermal low dominating the interior. We know that in winter you'll have the Kalahari high pressure dominating the interior. So the heat low or thermal low dominating the interior also shows us that these are typical summer conditions. What else do we have? We see that our high pressure systems, what's this, your mid-latitude cyclones, are a bit further south, not closer to the interior, and your high pressure systems as well are a bit further south as well, not in the interior. What else can you use? What else you can use is that we have a tropical cyclone known as Ghislaine or Ghislaine or G-Lane, whatever you want to call it. So that's the tropical cyclone you have coming or approaching Madagascar there. So this is Madagascar. So tropical cyclone is approaching Madagascar, and we know that these systems occur late summer, early autumn, right? So that's when they occur. So that's one piece of evidence you can also use. So the mid-latitude cyclones down here are just distractions. So remember, these systems occur throughout the year but affect South Africa in winter, and so you must take note of that. So if you see a synoptic map and you see mid-latitude cyclones, that does not necessarily mean that those conditions are typical winter conditions just because there's a mid-latitude cyclone. You must look at other pieces of evidence, and the dominating pieces of evidence suggest that it is summer. And what are those evidences? It's the date, it's the thermal low, and the tropical cyclone, and the location of your high pressure systems. They're a bit further south, including your mid-latitude cyclones as well. Yeah, so those are pieces of evidence you can identify. Now in winter then you'll have a different situation. Now continuing to count, from March, April, May we have autumn. From June, July and August we have winter, and the date here is 2009 August 15. So this is showing us that it is still winter conditions being depicted here. Now you notice that we don't have a high pressure at the interior dominating there. but it does not necessarily mean it's not winter, right? And why do we say so? Simply because the high pressure systems, South Atlantic high pressure and South Indian high pressure, are influencing the weather in the interior. So if you look at the patterns, the isobaric patterns over there, they extend towards the interior. If we just sort of follow them through, I hope this is as neat, just to show you that these high pressures extend towards the interior. If you look at that, right? So this is showing us that they are indeed dominating the interior. And here we also have a coastal low, and remember that a coastal low occurs just before berg winds will occur, right? And remember, before berg winds occur, we usually soon after we usually have a cold front approaching and affecting the coast soon after that. And another piece of evidence is just that your mid-latitude cyclones are approaching the interior in families or subsequent to each other. They are closer to the interior, so that is suggesting that this is a synoptic map showing typical winter conditions. So I hope you understand the charts and how to differentiate between summer and winter. Now looking at the weather components then. The weather components that you can have in a synoptic map, you have weather stations. And remember, you need to be able to read the weather stations. We said the circle represents cloud cover. We said the temperature on top is your air temperature or your atmospheric temperature, and the dew point temperature is usually below. And remember, dew point temperature is the temperature at which condensation starts. And then you also have the symbol in between the two temperatures, and that is representing the weather at that particular time. Now, if you have instances where there is no symbol, that is showing you that there is no precipitation. So please take note of that. And we also have wind speed being represented by the arrows there. And according to that, the two arrows are both long. So it is showing us that it is 20 knots over there, right? So please remember that. And we also have the wind direction represented by that. Now you see that it's skewed to that direction, which means we have northeasterly winds over there. So please remember that. Now you then also need to be able to interpret these weather stations, right? Now the first one is representing typical summer conditions, if we can put it that way, and the second one is representing typical winter conditions. And why do I say so? Now at some points you'll be expected to give reasons as to why the temperature is like that, why the dew point temperature is like that, why the wind speed is like that, why the wind direction is also like the way it is, and cloud cover and precipitation. Now if you look at this weather station, you can see that the atmospheric temperature is 32 degrees Celsius, and it shows us that the temperatures are high. And why are they high? So you must know that firstly, temperatures are usually high in summer. And why are they high in summer? It's due to what? Due to terrestrial heating, right? Now terrestrial heating is usually the cause for high temperatures, right? While in winter, when you have high temperatures, what is the cause for that? It's usually adiabatic heating as air descends. So adiabatic heating may lead to you having high temperatures while the dew point temperature is really low. So remember, air temperatures basically focuses on how hot or cold the air is. And when temperatures are low, such as in this case, this is showing us the cooling of land, and remember we have a cooling of land in the winter season, and what causes that? It's the fact that the earth is receiving oblique rays from the sun. So if you are asked to interpret a weather station and give reasons, you need to think about these reasons at the top of your head to say, oh, temperatures are high, possibly because of adiabatic heating, because the synoptic weather map is showing winter conditions. But if it's showing summer conditions, you can say, oh, temperatures are high because we are receiving direct sunlight from the sun, and because of that, we are facing terrestrial heating, which leads to temperatures being relatively high. Right, and looking at then dew point temperature. Now, dew point temperature, first, for starters, you must know that dew point temperature is the temperature at which condensation starts. And you must know that when there is a big difference between the air temperature and the dew point temperature, this means that this air is dry. So there is little chance for rain, and that usually happens in winter. So when there's a big difference, for example, the difference is 12 and -7, so there is a big difference between the two. So it shows us that these are typical winter conditions, which means we can't have rain as a result. So in summer, moist air rises, and we know that after it rises, it results in a very high dew point temperature. And in winter, there is less evaporation, right? So we also have subsiding air, so the humidity rate decreases, and that is why we may have a lower dew point temperature in winter. Then thinking about wind speed, you must note that wind speed is shown by the feather. So a long feather, such as this one, represents 10 knots, and a short one represents 5 knots. So if you look at the station, means we have 15 knots. In this one, we just have the short feather, and it represents 5 knots. So that's the wind speed. So the isobars are close together, and that is showing us that we have a steep pressure gradient and strong winds. So in a synoptic map, and when you have isobars being close together, that is showing us the wind speed, because remember, the higher the pressure, or the closer the the isobars are to each other, that represents we have a steep pressure gradient, and it means we have stronger winds, right? So those are all directly proportional to each other. While when the isobars are further apart, it means we have a gentle pressure gradient, and it means we are going to have gentle winds that range from 5 knots, 0 to 5 knots, as you had seen over there in weather station B. And then looking at wind direction, wind directions, remember, winds are named according to the direction which they blow. So when we have air diverging from a high pressure, we are going to have anti-clockwise circulatory winds, and that may influence whether these winds are northwesterly or southwesterly, or southeasterly or northeasterly, or southerly, northerly, westerly, or easterly. So please remember those convection. Now, air converging in the low pressure will lead to clockwise circulation of air. Now, looking at cloud cover, remember, cloud cover is indicated by shading of the circle. So in winter, we have limited cloud cover, so that's what weather station B is showing. While in summer, we have more cloud cover, which means we are more likely to have overcast conditions after the midday. So that's what we have in weather station A. While with precipitation, the opposite is true, of course, right? Precipitation is dependent on which pressure systems are dominant. So we know that in summer we have low pressure systems dominating. So remember, precipitation is represented by symbols. So since pressure systems are low pressure system are dominating, means we have more rising air, and therefore we are going to have more condensation, leading to thunderstorms and rainfall in summer, while in winter we may have snow as a result of anticyclones and extremely cold conditions being experienced. So that's what we have. This is showing summer, this is showing winter. So in winter you may have no precipitation, because remember you have stable weather caused by the anticyclones. So please remember those points. That's how you interpret a weather station. Now let's move on then to satellite images. So these are the components of a satellite image. Now remember, a satellite image is made up of an image with the following characteristics. So with satellite images we look at colors and physical visible features rather, that we talk about. Sorry about that. So we basically think about the colors that you may identify, right? So the visible features and the colors you may identify. Now looking at these diagrams, and this is showing us a satellite image of of a tropical cyclone or a hurricane. Now you can see that the colors I identified are shown there. So we have the blue, and the blue is showing us the ocean, right? The oceans. We have the brown. The brown is showing us pieces of land. We have the gray. Now the gray is shown in this other diagram. So the gray represents pieces of land, vegetation, and we can have black. Darker black shows the ocean and sections of vegetation. And we also have white showing us the clouds as well, right? And you can see we have green as well in the color one, showing us vegetation. Now those are some of the features we have: land, clouds, and the ocean. So synoptic maps, so your satellite images may show these components. The same is true with a different system. So this is a mid-latitude cyclone, and you can notice you see the same colors. A bit of blue there, a bit of blue that side, the white, the green and brown, and the gray here, and white for clouds and all of that. So those are the components you can identify. Now how do you interpret them? So you see that we have an opening at the center of this system. So this is showing us that we have the lowest pressure, and means air is converging towards the center. And since it's converging towards the center, it means now we have a low pressure cell. And we say this is the eye, and we'll teach you now features of a hurricane, of course, or of a tropical cyclones when we do tropical cyclones in topic number 2 of grade 12. And parts that are blue and black show us clear skies, right? So that's why we can identify the ocean in the blue sections or black sections. And we see that on the sides we have some clouds here. So this is showing us the eye wall of this system. And we also we have those features over there. Then let's think about the different lines, guys. So remember, with satellite image is so easy, so easy. You just identify which system it is, and you use how clouds are arranged for that. Now let's just think about something else: the differential lines that we use in geography. So the first lines we use is what we call contour lines, right? And before we look at contour lines, a lot of the lines we use start with the word iso, right? Isobar, Isohyets, Isotherms. So those are the lines we use. Now the word iso is a Greek word that means equal. So an iso line is basically a line that joins places of equal something, or places of equal points, right? Now going back to contour lines. Contour lines are basically iso lines joining places that have the same height value on a map. So contour lines are iso lines joining places that have the same height value on a map, on a topographical map and an orthophoto map. So this diagram is showing us that. So you see these brownish lines here, those are your iso. So those are contour lines. They are showing you regions of the same pressure, and they usually have values 440 and so on and so forth. So they are showing us places that have the same height value. And then what are isobars? Isobars are basically iso lines on synoptic weather maps that show places of equal pressure. So isobars, they're iso lines showing places of equal atmospheric pressure. So if you look at this is showing us an isobar, and you see that with a high pressure, we have pressure increasing towards the center, and the isobaric interval is 4 hectopascals, while with the low pressure, pressure is decreasing towards the center. And it's also proving us what pressure gradient says, that air will move from a region of high pressure to a region of low pressure, from high pressure to low pressure. And if you look at this, synoptic weather maps will always have your isobars over there. These are the isobars there, and they show places of equal pressure. And then what are isotherms? Isotherms are iso lines on maps that show places of equal temperature. So if you look at thermal maps, they usually show us your isotherms. So these are our isotherms in this diagram. They're showing us how temperature changes in the different regions, right? So the lines there showing the changes in temperature are known as isotherms. Remember, therm is an abbreviation for temperature. Think about the word thermometer. So in this diagram as well, we have isotherms showing us how fragments of the city may have the same temperatures while others may have different temperatures. When we look at the formation of an urban heat island, so we are going to look at this in the last topic of climatology. So you need to be able to identify these isotherms. And then we have isohyets. Now, what are isohyets? Isohyets are lines joining places that have the same amount of precipitation. So it may be the same rainfall, same snowfall, and all. So these are the lines. And you can see that the different colors are showing the mean annual precipitation value. So this is 2000 millibars, what's this, millimeters, 1500, 1.250, 1000, 1000, 1000, and so on and so forth. So those lines are showing us, or are joining places of equal precipitation. Yeah, so I hope you understand. Now, this basically marks the end of our revision. Congratulations, we are finally about to start with grade 12 content. You can clap hands for yourself. So if you have fragments of the videos of the work from part 1 of revision to part 4 that you do not understand, please make sure you go back and re-watch the videos. It's gonna help you, because you will not, and I repeat, you will not, never ever master this section if you do not have this prior knowledge that we've discussed from your grade 10 and 11 work. And I've sort of found a very nice way, an innovative way to represent the stuff. So please think about the stuff in that way. Remember, climatology is scientific in nature, and the questions you are asked in exams also want you to apply some level of scientific reasoning. So that's what is required from you. So please go and watch these videos. So for now, we are going to look at an overview of your climatology content for the year. Now, this is the climatology content you have for the year. Now, remember, the topic you guys are working on is known as climate and weather. Simply put, climatology. And remember, climate looks at the average changes in weather patterns in a particular region over a long period of time. Now, the word climatology is made up of these two words, climate and the word logy. Now, logy is the study of something, and since climate um, is the change in average weather patterns over a long period of time, it means that climatology is the study of the changes in average weather patterns over a long period of time of a particular region. So that's climatology. So we in climatology, of course, we do consider weather. So we are going to look at three topics of climatology, being mid-latitude cyclones, tropical cyclones, and subtropical anticyclones. We will then look at valley climates and urban climates, where we'll be looking at weather. Remember, meteorology is the study of weather on a day-to-day or basis. So climate and weather basically looks at changes in weather patterns over time. So with subtropical anticyclones, we'll be looking at the types now of anticyclones: South Atlantic, South Indian, Kalahari. With valley climates, we'll consider some core concepts, which is aspect of slope, what the inversion layer is, what force pockets are. With urban climates, we'll look at the concept of urban heat island and the pollution dome, how they inform each other and their interactions thereof. So that's what we'll be looking at in this section of work. Now, in summary, and I would just like to do that. Now, in summary, that's what we have for the year in climatology. So in the first, or rather in the next session, we are going to be looking at the first topic of the year being mid-latitude cyclones. We are finally starting with grade 12 work. Please do join the session, and I hope these sessions are going to be of assistance to you. So please feel free to subscribe to this YouTube channel, like the video, share it with your fellow classmates. If you are a teacher watching this, please share it with your other colleagues and your learners as well, so that they find this climatology in a more simplified format. We are going to be teaching the work as if we are in the classroom, looking at all the aspects as per the examination guidelines released in 2021. So we are going to cover all aspects of the content. So you must note that in the upcoming sessions now, we are going to have content videos and activity videos where we show, okay, to say, now that we've taught you the content, all of it in order, this is how you approach examination questions with regards to that particular topic. So we'll be looking at both content and application of the different topics. So please join the sessions and hit on that notification icon so you are alerted when we have our sessions. Thank you very much. Bye.
Audio Jungle.